Good afternoon, everyone. It's just gone 2, so I guess we should probably start again. So the first session this afternoon is by Radu Popescu from SIVECO, Simavi in Romania. And he's going to tell us about the IMPETUS platform, which Matthew briefly mentioned in his introductory presentation this morning. So over to you then, Radu.
Hello, everybody. So I'm going to present some details and ideas about the platform that was developed in the IMPETUS project. I guess the information about the funding of the project was already mentioned. So the main objective of the platform is to collect and share information between security and emergency actors. The IMPETUS platform will serve as a central information hub, supporting security and emergency operations through providing analytics and user-centered visualizations of data collected from smart city systems, like sensors or computing and network assets. The main objective is supported by the platform through threat detection, classification and monitoring, and response optimization. Concerning the threat detection, IMPETUS detection capabilities include weapon detection through the use of AI-enabled CCTV cameras, biochemical contamination detection through air monitoring, and cybersecurity detection. Concerning threat and classification monitoring, IMPETUS will use artificial intelligence and data fusion for anomaly detection and pattern recognition, allowing smart city operators to rule out false alerts and only focus on real threats. About response optimization, IMPETUS will optimize human-computer interaction, for example, visualization tools, operator, cognitive load monitoring. And it will facilitate communication between city stakeholders and towards the public, for example, through social media alerts. The platform is developed with the following characteristics in view. Modularity. This means that the module operations are kept separate so they can run independently and potentially be swapped out or replaced by other modules in the future, if this is dictated by the evolution of the platform. Another characteristic is module interoperability, and for this a common data format is used for data exchange between modules. The platform is open and extensible, and it is future-proofed by using a set of application programming interfaces, which can be used by third-party developers to add new functionalities to the solution without requiring a major redesign of the platform. Also, the platform is using IoT and cloud computing approaches that will reduce risks associated with excessive centralization of large amounts of smart city data. The platform provides capabilities like access control, alerting, internal and external integration, security, and data visualization. We'll explore these capabilities in the following slides. The platform implements access rights based on roles, meaning that within the platform, users have associated roles which allow access to certain features and functionalities. The platform uses access control policies that enforce who can access information, where and when. By being a web-based platform, it supports simultaneous users connected. The platform is using key clock for authentication, and this technology comes with features like single sign-on that is useful because the platform integrates a set of tools, and the user can log in once and access the user interfaces of the tools that support this feature without authenticating again. Another feature is LDAP and Active Directory integration, so the platform can connect to existing user directories and reuse the roles already defined. Keycloak also supports standard protocols like OpenID Connect, OAuth, or SML. Keycloak makes possible to centralize the management of users. Another capability of the platform is to manage the alerts received from various sources. The platform integrates tools specialized on different security aspects of smart cities, like weapon detection, cyber threats, big data analysis. The alerts raised by the integrated tools are centralized and presented to users in dashboards. The dashboards can be tool-specific and present the alerts from one tool only, or they can be general dashboards that aggregate alerts from multiple tools in order to give an overview of the situation. This is an example of how a list of alerts from different tools and with different criticality levels can look. The platform is still under development and feedback is gathered from project partners. And based on this feedback, new ways of visualizing the alerts will be created. For certain tools, the alerts will be divided in two categories: technical alerts, operational alerts. As an example, in case of the human-computer interaction tool, a technical alert can be a sensor that is disconnected. An operational alert is raised when a high level of stress is detected on an operator. As another example, in case of the biological risk detection tool, a technical alert can be when the level of chemicals used by the device are too low and they have to be replaced. An operational alert is raised when the concentration of bacteria is high. When an alert is received by the platform, the user will be able to react to it in various ways. For example, the user can access the tool that triggered the alert by clicking on a certain button on the interface. By accessing the tool, the user can see more details about the alert. In this particular example, the user can access the stream from the camera that triggers the alert. So the user clicks on the button, show live cam, and he will have access to the live streaming. Another possible action that the user will be able to take is to open an application installed on their computer, application used in the emergency response process, or the user can open documents like manuals or procedures with checklists to follow in case of emergency. A few words about the internal integration. The platform is modular. It integrates a number of tools defined in the project, but individual tools can be added or removed without disturbing the functionality of the platform. Individual modules can be swapped and replaced so that the platform does not depend on the performance of one module. The statuses, alerts, and support information from tools are centralized at platform level, so the platform is responsible with data integration. Also, the outputs of the tools are combined in order to derive new information or to raise the alert confidence level. So we can say the input data is enriched. So the platform is more than the sum of the tools. The communication between the tools will be standardized by using a platform-defined data format in order to ensure interoperability. In order to achieve its objectives, the platform should be always in operation and should be protected from outside intruders. The security is an important aspect in the project, considering that the tools and the platform work with city data, some of which is private or sensitive. The security is implemented by following best practices in the area, like using latest releases of base software, like databases, web servers, operating systems. Another best practice is to train the users of the platform and raise awareness on the security considerations. In this regard, we should mention that the project will also produce a security framework adapted to the project partner cities. Another best practice is to protect the data in transit and in storage through techniques like encryption, anonymization, or obfuscation. The platform and the city infrastructure will be assessed for vulnerabilities using one of the tools involved in the project, namely breach and attack simulation. And the platform will be GDPR compliant. Considering the external integrations, the platform will support external integrations in the following ways: by sharing information with other trusted organizations which are not part of the IMPETUS operating environment. As a special case of such information sharing, the IMPETUS platform can send alerts to operators across different organizations. The IMPETUS platform interacts with existing devices and platforms in the cities. The user experience is considered in developing the platform. So the IMPETUS platform will be available in multiple languages. It will provide aggregated data and diagrams to allow for strategic monitoring and planning. The IMPETUS platform will adopt a common terminology and symbology in order to make it easier for the users to learn. And the platform will support different forms of interaction depending on the situation and user profile in order to minimize the cognitive load of the operators and decrease the reaction time in case of emergency. This is a logical overview of the IMPETUS platform. The platform integrates data and alerts from 9 tools. The data collected is presented to the user through a common front end that will contain big data visualizations and alerts from the tools. The user interface is organized as dashboards specific for tool or user role. It is possible to access the tool's own user interface for more in-depth data exploration. The tools work with data shared by partner cities. The data comes from their agencies or sensors deployed in the cities. We have found that there exists a solution that corresponds to this logical architecture, and this solution is the result of a Snap4City project that is a complex project developed as an R&D project funded by EU. The general architecture of this solution is presented here. Without going in much detail, I will just mention some key aspects, like it supports integration with multiple data sources, from databases, HTTP services, to MQTT or AMQP brokers. It contains a dashboard builder. The dashboards are designed to be used on screen walls in control centers, and they can be filled with widgets that can present static or dynamic data. The dashboards allow interaction with the operator. From the dashboards, it is possible to also produce data, not only visualize the data. This platform uses open source and well-established technologies like Keycloak, MySQL, Node-RED, NiFi, Elasticsearch. It has flexible deployment options that can adapt to various volumes of data. This is an example of how the dashboards are visible in the platform. Our approach was to create a dashboard for each tool that raises alerts. We can see here dashboards for each tool, and to create specialized dashboards for different categories of users, like operators from SOC or supervisors. You can see here some examples. This is a dashboard for one of the tools integrated in the platform, and we can see that it is possible to combine textual information and graphs. This is an example of a dashboard that contains widgets from multiple tools. For example, these are widgets from weapon detection. This is a widget that presents data from biological risk detection tool. This is a widget that presents alerts and notifications from physical threat detection tool. In the SOC, it is useful to have the information centralized. The user will be able to access the dashboards of the tools or the tools themselves for more in-depth analysis. This is a quick representation of how widgets can be added to a dashboard and configured. Here, together with the partners in the project, we are exploring useful features to implement in the platform. One such feature is the possibility to monitor multiple cameras in case of a weapon detection alert. The user will be able to monitor the camera that triggers the alert, but also cameras that monitor locations in the vicinity. Another useful feature will be the possibility to monitor the workload history of an operator, and also to filter the data from specific operators. Here, a console corresponds to an operator. Here we can see an example of data ingestion using Node-RED. Node-RED is a tool that uses the visual programming paradigm. It supports blocks that implement various functionalities. The way the blocks are linked describes the processing of data. In this case, the data is pulled from Kafka. It is transformed in the proper format for saving, and then the data is stored in a database, and it will be accessible in the platform dashboards. Okay, so that's all about the platform, IMPETUS platform for now. If there are any questions.
Okay, any questions for Radu? A few things I would like to ask Radu. when you use the Snap for City platform, was it a big learning curve to adopt it, or did it take you a long time to really get a benefit, or did you get the benefits fairly quickly?
Well, this is a complex tool with lots of documentation, so we have to, there was a necessary amount of time to familiarize with this platform, but also it shared a lot of the tools that we planned to use anyhow. So it took a while, but not so long.
Okay.
Let's say it like that.
I mean, I guess when you use something complex, you shouldn't expect to unpack it and be able to use it fully on the next morning. So I guess is what you would expect. Yeah. You mentioned at one point the thing about exchanging data between the tools, and that there would be some kind of standard format for doing that. And I was wondering if there exists or is being developed any standard for exchange of this type of information on a broader basis than what we might be doing in the project. Do we know of any work in that area?
Yes, we are working in defining a common format for the data that will be exchanged through Kafka. This format should be sufficiently standardized in order to integrate easily the tools, but should be also extensible in order to be able to integrate in the future new tools in order to respond to one of the requirements of the platform to be extensible. So yes, we are working on defining a data standard, data format.
Well, what I was really wondering though, Radu, is whether this is something that we're doing alone or whether there is any other work on this kind of thing for this kind of data that we know about, people that we could cooperate with outside Impetus. Do we know of anything that's going on?
Well, the Snap4City platform supports and integrates Orion Broker that defines exchange of data based on JSON LD format. So we can say that there is some work that has been done in this area by others. We should mention that Orion Broker is a part of the Fireware ecosystem that was also developed with funding from EU. Yeah. So as the project progresses, we will also explore if the communication between the tools could be based on this format. The way we started the integration was based on Kafka. Okay. But we are not limiting ourselves to that. If the opportunity appears, we can and we will use JSON LTE and Orion Broker.
Okay, in that case, I think we say thank you very much, Radu.
Thank you.
We're 5 minutes ahead of schedule now, so we can move on, I hope, to the next presentation, which is called Big Data Ingestion and Analytics for Physical Threat Intelligence. And I understand that this is being presented by Paolo Mignone.
Good morning, everyone. Thank you, Joe, for the introduction. I'm presenting a work within the IMPETUS project scope. I'm Paolo Mignone from Cini, which is a research partner of the project. And I'm presenting big data ingestion and analytics for the tool Physical Threat Intelligence. Such a tool aims to support law enforcement in establishing timely traits and anomalies in advance, of course, also by exploiting sophisticated automatic systems. Of course, the IMPETUS platform will make it possible to enhance the security of the cities involved in the project, such as Padua, and also, but also the platform can be replicated since It is a very general pipeline, and our tool is able to work with different kind of sensors. It depends on the kind of data that the sensor provides. If they produce, for instance, time series and they are geo-distributed. Of course, we are able to get some time series data. So we need the information of the time point when some measurements are performed. Of course, this measurement could be calculated, could be computed through georeferenced sensors that could be located at different places of the city. And the aim is to perform multivariate analysis, mainly by considering two different tasks. The anomaly detection, which is essentially useful to identify some values which could be anomalous with respect to historical data, and it is performed in an unsupervised manner, while the event classification allow us to identify specific kind of traits from data that could be done in a supervised fashion. We can work with different kind of sensor. For instance, a urban traffic camera is able to produce metadata that could be exploited for the analytics purpose. For instance, we can analyze the level of traffic or the pedestrian trajectories from such cameras, but also meteorological sensors are useful to analyze weather conditions by considering several variables such as wind speed, direction, the temperature, and so on, that could be useful to analyze. We analyzed also data from air pollution sensors for both the cities that are useful to catch some useful variables such as atmospheric particulate matter of different sizes, ozone, and so on. Of course, we also considered data from levels of pollen that could be measured through pollen sensors, and such data are considered from ARPA Veneto website, which collects not only air quality data, but also the level of dangerous pollens divided by families. This is an example of sensor metadata. So we need the timestamp when the current measurement is performed for a set of variables under analysis through such an example, for this case, a camera. And of course, we have the possibility to recognize the place where such a measurement is performed, for instance, by considering a pair of GPS coordinates. We can extend our unit of analysis by connecting the same time point through heterogeneous sensors. So we can extend our unit of analysis not only to analyze traffic levels or trajectories of pedestrians and so on, but also air temperature, humidity, air pressure, and also particulate matter, CO2, and the level of dangerous pollens in the air, for instance. So this is the scenario, an example of anomaly detection task. We can analyze multiple time series from georeferenced sensors, not only indicated the traffic, but also other kind of variable that could be useful to analyze. And then we raise an alert, we generate an alert to be shown within the SOC operator interface. This slide presents a conceptual view of the overall architecture. The scope of the architecture is to collect and maintain data within a data lake using an advanced ingestion procedure, which increases the data governance by preparing data depending on a set of policies that are predefined on data sensitivity and the user access rights. Analytics then can be executed over prepared data, being sure that the correct degree of privacy is preserved. More in detail, the entire processing chain can be divided into ingestion and analytics procedure, where the analytic procedure receives input from the ingestion procedure. In both the two procedures, data can be stored, and data storage is performed within the data lake. We note that the data lake contains just data that are sanitized before the ingestion procedure. Okay, in this slide, we describe how we implemented our architecture using the Apache framework. It also shows the details on the ingestion procedures, of course. Our approach considers data sources to be annotated prior to be ingested, which express, for instance, the sensitivity level in terms of privacy of specific features. The ingestion procedure is driven by a set of policies considering the annotations on the data and the identity of the specific user or service which ask for the ingestion pipeline. Our policies are focused on triggering a specific data transformation taken from a taxonomy of transformations, depending on the data sensitivity and, of course, on the user or service which is requesting the ingestion pipeline. We note that the ingestion request is triggered anytime an analytic is triggered from the same user. So in most of the cases, the user and the service considered for the ingestion is the same user that want to execute also the analytics. So it is intended to use the whole pipeline before to produce a result to the visualization pipeline through, for instance, Apache Kafka Queue. So the ingestion procedure is responsible to collect and ingest structured but also unstructured data. The data management is based on ingestion time access control, which is essentially attribute-based policies, is performed through attribute-based policies. Imagine we have an attribute which indicates the data, the sensitive data. So we need to understand how to handle such a sensitive data, for instance, by using hashing function or obfuscating them and so on. Based on annotation modeling sensitive data, and then we can enforcing the transformation, for instance, data sanitization before the analytics procedure. The analytics procedure is divided in 3 stages. In the first one, the initialization stage, we train our PTI tool using a data collection that are exploited through distributed machine learning techniques, which works with different computational nodes. For instance, we can exploit deep learning self-organizing maps in an unsupervised manner, but also if we have annotated data, we can perform predictive density clustering. The second one is the identification stage, where the PTI tool is able in production to detect anomalies from sensor data. And the third stage is the model adaptation stage. If we have a pre-trained predictive model, we can exploit it after the initialization stage, and then we can adapt its behavior to new situations using the latest recent data. We performed different experiments. For instance, here we analyzed a time window of data from 2014 till 2019. Such a data indicates and describes the environmental information for the city of Padua. We exploited the data of measurement, the air temperature at 2 meters. We considered the average, the minimum, and the maximum temperature, the precipitation in millimeter, humidity, and concentration of allergenic pollens in the air. We extended the anomaly detection task for the purpose of the project to be more interpretable. For instance, we are able to also rank the most important features, which means the most important sensor or the most important variable under analysis, which most contributed to raise an anomaly. This is an example of real scenario to better understand this peculiarity, this particular functionality. We could be able to better understand what is happening in this particular car accident, since the level of traffic is representing the most contributing variable under analysis to raise such an alert, and so on for the concentration of pedestrians in this particular street, which is quite abnormal, the CO2, temperature, and so on. Here we are showing different graphs that are perfectly aligned with our raised anomalies. We detected, for instance, an anomaly of a level of pollens for the 5th of April in 2014. And we saw that such an anomaly is perfectly aligned to several peaks in these graphs related to pollens. Of course, we performed the further analysis for Padua. We performed the vehicular traffic flow analysis, and for Oslo, air quality monitoring by considering different air quality pollution indicators. In conclusion, our method for the anomaly detection task is able to catch anomalies within the data, allowing us to identify also such anomalies when they are usually rare. The method was fruitfully exploited to detect anomalies for the air pollution quality of both the cities. And of course, qualitative analysis showed that our method is able to catch levels of air quality that could be anomalous with respect to historical data for both the considered cities. Also by considering the information of the geographical place of the sensors, and also the current situation with respect to the past. This means we exploited the spatio-temporal autocorrelation within the data. These are further readings where we acknowledge the project impetus that you could read. And this is the set of references useful to write this presentation. Thank you. From my side is all.
Thank you very much, Paolo. Could I ask you, Paolo, about you mentioned these anomalies in the data in Oslo and Padua. But what's not totally clear to me is, would these anomalies have been noticed by some other means, or was this some anomaly that really demonstrated that this approach notices things that might have been missed otherwise?
So our tool was able to catch some anomalies from unsupervised data. So we do not have annotated data to perfectly say, okay, we catch anomalies with respect to the specific annotated data as anomaly. So in this case, we are exploiting geometrical approaches to compare historical data that we considered as normal window to train a predictive model of a stable situation, And then we tested our tool. It's always in an unsupervised manner because we haven't annotated the data to catch some particular anomalies. In this specific example, we can see that we detected peaks, but as I told you also in other presentations, here we are not saying that this is the most contributing variable to raise the anomaly, but in reality, we are saying that this one is the most contributing variable to raise the anomaly. In this case, I'm not showing here, but we have also a ranking here to show who is the most contributing anomaly. Of course, here we are raising anomalies with respect to peaks, but we are able also, as in this case, to show anomalies also when the combination in a multidimensional setting, the combination of variables is anomalous. This means that, for instance, also values, low values could be considered as anomalous with respect to historical data. Of course, the assumption is that we are training the model in a normal scenario. So imagine we have 1 month of timing window to train a predictive model in a normal scenario. Okay, in this month we haven't anomalies, and then we can train our model. Of course, we can do it also offline with a batch of data, historical data that could be saved in a repository, let's say. And then after training our model in a normal scenario, we can use it in production to understand if the current data are going far away from the historical ones. I don't know if I answered the question.
No, yes, thank you. That was good. Could I just ask you quickly, when you say historical data, how old is history? A month, a year, 5 years?
Okay, it depends on the granularity, the kind of granularity axis. So if we have, for instance, 1 day of data that is computed per millisecond, and our aim is to detect something per hour, okay, here we are working with this granularity. But if you intend to raise anomalies for a week or for a specific day, we can extend depending on the kind of data that we have. So here we are exploiting the time as another feature, as another variable under analysis. This is encoded within data.
Okay, thank you. I see that Mathieu has a question.
Yep, thank you, Paolo, for the presentation. So you presented this big data approach, and I was wondering, you gave examples from different kinds of sensors and data collected across the city. If we push this sort of smart city logic and think about all kinds of data collected around the city, supposing that you have access to them, does the approach scale easily, or what are the kind of barriers that you would technical or potentially logical barriers that you run into if you try to scale up to other kinds of data?
So okay, here we have potential bottleneck, of course, depending on these channels. Of course, for data sources, if we have 1 measurement per hour, we have to collect them at this level of speed. And then here I can say more about the scalability, of course, because we are working with these technologies, Apache Spark based. Apache Spark allows us to scale. So because we have, for instance, 5 machines in a cluster of machines or 10 machines, cluster and this technology allow us to share partial results among machines in a scalable manner, since this aspect is already tested, and Apache Spark do properly this work. Of course, by sharing and avoiding that the overhead of communication among machines is worse. Let's say is worse than the analytics on the huge amount of data that we can perform. This is mainly done within the analytics pipeline, of course, through policy-aware ingestion pipeline and analytics pipeline. Here we have a Hadoop file system, which is a distributed file system. So this is a framework that is well suited in literature to work in a scalable manner, and we also tested such a peculiarity in a good way, let's say. But this bottleneck, of course, we have the speed that we can have with the data sources which provide the data to ingest, let's say. Okay.
Yeah, thank you.
Yeah.
Well, thank you very much, Paolo. I don't see any other questions, so I think we say thank you to you, Paolo, and we move on to the next presentation. The next presentation is from Joaquin Luzon from Insect Intelligence in Barcelona, and he's going to talk to us about ethical challenges in social media AI-driven threat detection for cities and citizens. So please, Joaquin.
Hello, thank you, Joe, for the introduction. I'm Joaquin Luzon. I work for Insect Intelligence, and we are developing one of the tools that are going to be, or that are being integrated in the toolkit that is conforming the technology module of the IMPETUS project. I would like to talk about the ethical challenges that one of the technical developers and how we address them. First of all, as transparency through explainability is one of the key aspects for ethical AI, I would like to give some context about ourselves in Insight and who and what we do. Insect Intelligence is a company conformed by AI researchers and developers, and we collaborate with government, law enforcement agencies, and other institutions such as municipalities to find answers and help them to save lives. Our company was created 5 years ago in Barcelona, but we work globally, and we are research focused as a technological SME that has been awarded by 3 Seals of Excellence by the European Commission. Our focus is to prevent radicalization and terror, disinformation and misinformation, hate speech and threats, financing of terrorism, detection of criminal activity, and to help organizations to monitor the public opinion and their brand reputation. Our methodology consists on social network analysis, which I will explain further in detail. And our technology is based on natural language processing methods, and we are powered by deep learning and machine learning technology. The social media detection tool, that is the tool that we are providing to IMPETUS. It's an ethical-based monitoring tool to be used in the context of security in smart cities. One of the challenges that we have in this project is that we must be flexible as possible in order to adapt our tool for the necessities of the municipalities without initially knowing the domains that it will be applied. For us, the acceptance pilot that we had the previous weeks helped us to understand and to be more flexible and adapting to the necessities of the cities. First of all, we will talk about the extractions that the social media detection tool does by applying natural language processing. We have the concepts that are the verbs, nouns, and adjectives that are contained in the social media messages or website contents that we gather, we collect. This is an example. There are the entities, which are locations, person, or organizations that the messages contain. There are the topics, which are which is a categorization of each of the messages by a predefined list of 300 different topics. So, for example, in this example, we categorize the message as a message that is talking about the topic of music. Then we have, this is not correct, should say key ideas. These are the key ideas, which are a combination of the previously explained concepts in order to form more specific ideas. And the hashtag, which are very useful for us to identify trends or open or alive conversations through the social media platforms. We use front end that let the user to understand how all this data is processed, and that shows the classification of the models of the messages by our models in different areas, such as sentiment, significance, and hate speech. Talking about sentiment, the messages, every message is categorized in between -5 and 5, showing what's the overall sentiment of the message by an analysis word by word. We can see an example of a message that is expressing a negative sentiment or a message that is expressing a positive sentiment. Hate speech is detected by a detector that is built of public models consisting of billions of parameters. These public models are fine-tuned to we fine-tune a model that contains pre-trained annotated data and calculates the probability of a text, a text containing hate speech. I would like to highlight that containing hate speech is not the same as having a negative sentiment. For example, in here we can see a negative message that contains less hate speech than a message that is not specifically written expressing a negative sentiment. Then we have the significance score that for this project, we are talking about the engagement, which is the number of reactions that this message on a specific message is having in social media. And also, as I was talking about, as I was talking before, we have the social network analysis that calculates different series of metrics. One is the activity, calculates also how influence a specific user has in this network, and the text spreaders. As a network, as you can see, is shown like this in our tool, and it's a graph that consists of nodes and vertices and edges. The metrics help the user to understand which role each of the users plays in the network. And one of the key aspects or the key results that we can extract from the social network analysis is the disruption of the users by seeing who are the amplifiers, who are the influencers, which users have most of certain interactions, which users generate and keep alive conversations, which users act as external influencers, or which users are not able to engage even if they contact or try to contact with other users in the social media. So now that we have explained a little bit how our tool works, we would like to focus on the challenges that are made patent by the guidelines for ethical development of AI and big data systems. And for us, one way to assess if we are working in a good direction in order to address these challenges is to ask ourselves, are we being compliant with these guidelines? So I will use as a base of my presentation, I will use these guidelines in order to show how we work in addressing and assessing these challenges. First of all, human agency, liberty, and dignity. The challenge for us is to enable the ability for humans to be autonomous and self-governing. That's why our tool has a human-in-the-loop approach. So our models don't take autonomous decisions, let the user to understand the information that is provided in our tool, the analysis that are done in our tool, by having a training, a previous training for the user that help them contextualize all the information that they are seeing in the UI. Another challenge is the technical robustness and safety. We must ensure that the tool that we are developing is safe and secure. That's why we ensure and we make sure that security and robustness is applied to all our systems by the use of cloud services that are ISO certified, to establish a well-defined user profile management, and to ensure that the connection to our servers are made using protocols such as HTTPS, TLS, and SSH, using VPNs in all of our systems, using a firewall, and we perform a continuous scanning for in order to detect vulnerabilities in our systems. Privacy, data, and governance, or to make sure that the system does not violate or infringe upon the right to privacy, and that privacy sensitive or personal data is well protected. The key to this is data management. So when a user creates a project to gather and analyze data, we make sure that the data is strictly limited to this project, that the access to this data is strictly limited to the users that have access to the project, not anyone outside the organization or the set of users that has access to the project. We ensure that all data is deleted after the project is deleted or after a specific period of time. And we ensure full data anonymization from its acquisition, and only pseudonymization is granted for specific and authorized authorities or LEAs. In the case of pseudonymization, the de-anonymization of the data, it's only possible if the user is authorized and introduce a specific reason and motive and justified motive for the decryption. Diversity, non-discrimination, and fairness. The challenge is to identify bias in artificial intelligence models and remove it. So how we do this? We input models with what it should be considered neutral input and check if this is true. So for example, in this example, for example, a model that introduces bias would be a model that when we introduce the sentence "I am heterosexual," detects no hate speech, and when the message is "I am lesbian," it detects a high amount of hate speech. So in that case, the model is introducing a bias, and we should work in debiasing the training data set and optimizing the algorithms. How we debias the data sets? One way of debiasing is by replacing all the sensitive terms by protected groups by generic ones. So, for example, every time that heterosexual, lesbian, or other kind of sexual orientation is mentioned, it is substituted by sexual orientation, a generic term. This can be applied by many terms in the text. Also, in order to ensure the debiasing, we consider that the annotators for the training data must be gender, national, and religious diverse. This will enhance the fairness of the models. And also, for the specific case of hate speech detection, we optimize precision, and we not focus that much on accuracy or recall. Transparency. Make understandable how our tool achieves its decisions. Our tool always shows the original text to the user so they can understand why our analysis had reached a decision. And also, as I was explaining before, the user should, or no, not should, must have a detailed training before using our tool. That's why we always provide with a user manual and other guidances to the users before they access to our tool. Individual, societal, and environmental well-being. To reduce the harm possibly caused to individual, societal, and environmental well-being. In order to guarantee this, we have worked in the quantization of our models. So we can make smaller models that consume way less energy in the production environments. By using quantization, we have reduced up to 70% the size of the models from 1 GB to 300 megabytes. And that's all. As the only reference for this, it's the guidelines for development of AI and big data systems.
Thank you very much, Joachim. Does anyone have questions for Joachim?
Thanks, Kimi, for the interesting presentation. It seems a complex and a comprehensive tool for the social media detection analysis. And one of the last challenges for the AI ethics that you mentioned was related to transparency and the use and the need for the users to be trained before using this. So I was wondering when you tested this in the cities in Oslo and in Padua, how it has been perceived from the operators, and also what were the initial reaction and feedback for this tool?
Okay, so from the feedback that we gathered from the acceptance pilot about the understandability of our tool, I think that we can talk about two different aspects. First of all, the feedback that we got regarding usability of the tool was that it was easy to use, that professional that is familiar with the monitorization of social media can use the tool without a very detailed training, at least for the first analysis. But we have also received the feedback that in order to understand many of the extractions and analysis that the social media tool does, it is necessary to have very detailed and to have, let's say, some time for the user to assimilate all the concepts, all the analysis that the tool can provide and will provide.
Could I ask you, Joachim, at the very end, you mentioned this reference on the guidelines on use of AI and so on. Do you have any idea if this is something that's going to be evolving and extended, or is this going to be it for a long time?
No, in fact, we are aware that this is something evolving, as also AI is continuously evolving. So we also work in detecting the new initiatives and the new challenges that are made aware for the European citizens, so we can also address them.
Okay, thanks, Joachim. I see also there's a question in the chat here from Sandro. And he's asking whether what you're presenting will also be a basis of requirements for all kinds of AI tools.
I think it must be, since also these guidelines are going to be influencing and used in order to build and to make the next EU regulations. So I think that all the AI tools that are being developed must be compliant with these guidelines.
And perhaps a slightly tricky question, but so I think you've convinced as well that in building this tool, you pay great attention to making sure that the way the tool operates complies with all of these regulations and ethical values and so on. But something that you as a tool developer don't have control over is how some people might choose to use the tool. You know, if some public authority or police or something detects some reason to be suspicious of a group of people, and then they make decisions like, okay, we're going to ban this demonstration, or I don't know, they make decisions that perhaps they shouldn't. Might that unfairly give you a bad reputation, because people will say the police made this decision based on INSEAD's tool, therefore it's INSEAD's fault for creating such a tool in the first place?
Yeah, I understand that the challenge that of us to have to provide a tool that must be used fairly. We design our tool in order to be focusing on detecting threats and not to profiling people. So we developed our tool with taking this into account.
Yeah,
I
get
that it is a challenge for us. Yeah.
Yeah, but I mean, I guess you could ask the same question to all kinds of tools.
Exactly.
And technologies.
Exactly.
You know, the people who make kitchen knives could be accused that kitchen knives can be used for purposes other than cutting the meat and bread. You know.
Exactly.
Okay.
Exactly.
Yeah.
I have a question. I'm curious, could you say a bit more and a bit more details? I'm curious about the sort of the interaction between the technology and this advanced technology as a support for decision making, and what the experts do and know how to do relative to sentiment analysis and those kinds of intelligence processes. How do you see the interaction happening? And where's, in your mind, where's the machine, helping tremendously, or where is the human really the main player?
So I think that the human must be always the main player, because as human in the loop approach that we have in our tool, what we want is to assist the professional and the experienced professionals to detect relevant messages during the day-to-day work. So it is, I think that one of the main challenges for them is to identify relevant information in big amounts, huge amounts of data. So I think that if, for example, the professional wants to focus on very negative messages that might express, might derive in violent actions, our tool may help or will help them to identify those negative messages. But again, I think that the user is always the main actor in detecting the relevant, not the relevant, but the threats by using our tool.
Okay, then. Thank you, Akim. I don't see any more hands raised or questions. So in that case, I think we should go to the coffee break. We are about 5 minutes ahead of schedule, but I think we resume the coffee after the coffee break at 15:35 as planned. Then Joe Levy of Synetic will tell us about his weapon detection tool from his company. And I noticed that he hasn't signed on yet, so I don't think we have to wait until the scheduled time, therefore, because we can't say we'll do it 5 minutes earlier. So let's say that we rejoin at 15:35 in accordance with the agenda. So see everyone then.